ICTP-SAIFR and IFT-UNESP. Today, we are glad and honored to receive Dr. Nathan Seiberg. Currently, he is a professor at the Institute of Advanced Study in Princeton, and his researches focuses on various aspects of string theory, quantum field theory, and particle physics. He has made deep contributions to the understanding of the dynamics of quantum field theory, especially two-dimensional conformal field theories and supersymmetric quantum field theories. Professor Nathan obtained his PhD at Weizmann Institute of Science. He is a member of American Academy of Arts and Science and also member of National Academy of Science. He has been granted multiple awards along the years, like Dirac Medal in 2016 and Fundamental Physics Prize in 2012. This is two examples of a large list. So if you are watching in YouTube or here at Zoom, you can type your question on the chat and you are gonna read your question during the colloquium. Once again, thank you, Professor Nathan, and you can start your presentation.
Thank you for inviting me. I just want to make sure that you can see the screen and the pointer.
Yes.
You see the screen once or twice?
Could you do again?
Out the screen now?
Yes.
Moving throughout the screen, perfect.
Out of the screen, yes.
Okay, so thank you again for inviting me to give this colloquium. It's a great pleasure and honor. I visited Brazil a number of times. One of them was Nathan Berkowitz invited me to a school, and it was enormously exciting. So I'm looking forward to the pandemic being over and then to visit Brazil again, and go back to normal and to life with travel and so forth. This talk will have two parts, as reflected in the title. In the first part, I'll talk about quantum field theory. And in the second part, I'll go beyond quantum field theory. That's the beyond part of the title. And since we have a diverse audience here, I thought I would start with a broad brush description of physics in general and quantum field theory in particular, and see how it fits in the general framework of physics. So starting very slowly, let's start with classical physics. And classical physics is roughly divided into two parts. The first part, which is also historically the first, is classical mechanics, where we describe the time evolution of a finite number of particles. And the people who initiated this study were Newton, and then followed by Lagrange and many others. And the description of classical mechanics, as you studied in your courses, uses ordinary differential equations. So this is a well-established physics chapter using a well-established math chapter. The second part of classical physics is classical field theory. So as we move from the left to the right, the number of degrees of freedom for the number of particles goes to infinity. In fact, in classical field theory, we have a continuum of degrees of freedom. And examples of such a continuum set of degrees of freedom is the electromagnetic field. At every point in space, we have an electric field and a magnetic field. This is a vector, it has three components, and they evolve as a function of time. And then classical field theory describes the evolution of the electromagnetic field, and this is done via Maxwell's equation. And here is Maxwell. Another example that I will mention also later is the velocity of a fluid. At every point in space, the fluid has some velocity vector, and the equations that describe the evolution, the motion of the fluid, are the Navier-Stokes equations. And even more advanced, moving to the 20th century, is the metric of space. And here the equations that describe the evolution of the metric are Einstein's equations of general relativity. And again, we have a very natural mathematical setting for classical field theory, just as here we had ordinary differential equations. For classical field theory, we have partial differential equations. So again, we see a well-understood subject in physics with a well-understood mathematical setting. And there are, of course, interesting open questions that people still make progress with, but this is more or less understood. Both of these fields, classical mechanics and classical field theory use various aspects of calculus. Let me say a few words about calculus because I'm going to use that later. I'd like to frame calculus as the language of classical physics. What are the characteristics? First, it was new mathematics, was invented by Newton. In fact, it was somewhat motivated. Newton's invention of calculus, and also Leibniz also invented it. Their invention of calculus was motivated by physics. They wanted, among other things, to describe the motion of bodies, how bodies evolve as a function of time. So they invented calculus, and then calculus found many applications in different branches of physics and in mathematics, even making its way to science, engineering, and these days it's even in the social sciences. This is very exciting because what it means is that calculus is a deep idea. And the criterion for a deep idea is it was invented to solve one problem, but then it turns out to have many applications addressing questions that were not even designed to be answered by the mathematical idea. So calculus was designed to solve some problems, but it turned out to have applications solving problems elsewhere. And this is the hallmark of a deep idea. Calculus is also a mature field. So let me propose a maturity test for a field. A field is mature and it's more or less understood when it's fully streamlined. And the way to test whether it's streamlined or not is to look at various textbooks and courses. And in the context of, in the case of calculus, when you go around the world at different universities teach calculus, different professors teach calculus, and there are various textbooks, but all of them follow more or less the same logical order. That's a sign that the understanding has been completely streamlined, and it was made as smooth as possible and as logical as possible. Let us move to the 20th century, and instead of classical physics, we're going to have quantum physics. And just as classical physics was divided into two parts, quantum physics is also divided into two parts. The first is quantum mechanics, which is the quantum generalization of classical mechanics, and it describes the time evolution of a finite number of particles. And this is a photo of some of the people who contributed to quantum mechanics. And again, there's a very natural mathematical setting. Here we discuss operators in the Hilbert space, so there are some functional linear methods. Again, this is more or less well understood. There's still interesting questions. People still find new phenomena, but more or less, it's a mature field. It is a mature field and it's more or less understood. Moving to the right, as in classical physics, we moved from classical mechanics to classical field theory. Here we move from the left to the right, again by adding the word field theory. And that means that instead of having a finite number of particles or a finite number of degrees of freedom, we have an infinite number of them. In fact, a continuum of degrees of freedom. So just as in classical physics, we have a field as a function of space. Here we also have a field as a function of space, and this field evolves in time. An example is the electromagnetic field. Just as classical field theory, we discussed how the electromagnetic field evolves in time. Now, the electromagnetic field is viewed as a quantum object, and as a quantum object, it evolves in time. And there has been a lot of progress over the last several decades in trying to describe quantum field theory from various perspectives. And there's still very exciting progress. I'll mention some of these things later in the talk. My own personal view is that just as here, we had a very natural mathematical setting. And in classical physics, we have a very natural mathematical setting for classical mechanics and classical field theory. Here, the mathematical setting is not yet in place. And one sign of it is that quantum field theory is not rigorously understood. Mathematicians are not yet happy with the rigor of quantum field theory. And I'll say more about that later. The fact that it's not rigorous is very important. It's not, we don't want rigor for the sake of rigor. After all, we are not mathematicians. But we want, if we cannot explain something to the mathematicians, I think it is our problem, not theirs. I think this means that we don't fully understand it. And once we have a better mathematical foundation and it's more rigorous, I think this will also give us new insights about quantum field theory. And I'll say a few words about that. So where is quantum field theory? Which problems does it address? My point is that it's everywhere. Quantum field theory appears everywhere in modern physics. The first place I would like to mention it is in the context of particle physics. It's the language of the Standard Model. It describes the elementary particles and the forces acting between them. It uses to interpret data in the LHC, and it's also being used to propose ideas going beyond the Standard Model that can be probed at the LHC. And it is enormously successful. Here's an example of one observable, the electromagnetic dipole moment. Theoretically, it's computed to be this number. Experimentally, it's measured to be this number. And this is amazing accuracy. Every digit here probes our understanding of quantum field theory and the Standard Model in more and more detail. It probes it with increasing accuracy, which is probes more and more subtle aspects of a quantum field theory. And the agreement here is quite spectacular. There is no other branch of science that has anything like that, such agreement between theory and experiment. And I take two lessons from that. One of them, even though quantum field theory is not mathematically rigorous, we really know what we are doing. If we can do a calculation and obtain such accuracy between such agreement between theory and experiment, that's not random. We're really doing something correct. The second thing for us as theorists is that the experimentalists are ahead of us. They have one more digit than we do, and we have to learn how to compute better to push our understanding and push the comparison. The second, so this is about particle physics. The second place quantum field theory appears is in condensed matter physics. In fact, over the last several decades, many ideas in quantum field theory originated from condensed matter physics and propagated or were imported into particle physics. Other ideas originated within particle physics and were taken over to condensed matter physics. So there has been a lot of cross-fertilization between these two branches of physics, but the problems are really different. Whereas in particle physics, we would like to describe the model of nature, the Standard Model. In condensed matter physics, we use quantum field theory as a description of the long-distance properties of material. We have many materials in the world, and we can design even more materials exhibiting different phenomena. And what quantum field theory is good for is to describe the long-distance behavior of the system. I'll say more about that soon. It describes the phases that the system could be in and possible phase transitions between different phases. Moving to the next application is to cosmology. Notice the length scales. Here we talk about tiny distances. Here we talk about almost everyday material, kind of distances of everyday distances. And in cosmology, we talk about the universe, even the universe as a whole, or the beginning of the universe at very early time. And quantum field theory is important in the early universe, inflation, and elsewhere. Over the last few decades, there has been a lot of applications of quantum field theory in string theory and quantum gravity. And here it appears, quantum field theory appears in three different places, which are really logically quite different. The first of them is that the string is a one-dimensional object. As it evolves in time, it sweeps a two-dimensional world sheet. And we have a two-dimensional field theory living on this two-dimensional world sheet. This is the first context where it appears. The second is the low energy approximation. If we look at string theory and we look at it at very low energies, it behaves a lot like quantum field theory. In fact, this is one of the reasons string theory is so exciting. It's so exciting because we know that at low energies, it's going to look like quantum field theory, and we know that quantum field theory describes our universe very well. So this is already a success of string theory. And finally, in some cases, quantum field theory gives us a complete description of the whole system, including gravity. So these are three distinct applications. Every one of them deserves its own colloquium, so I'm not going to elaborate more on that, except to say that this is another place where quantum field theory appears. So far, I gave examples in physics, but there have also been applications in mathematics, especially in geometry and topology, where ideas from quantum field theory completely revolutionized our understanding of problems in mathematics. So I put now a slide which mirrors a slide I put earlier about calculus. I'd like to propose the point of view that just as calculus is the language of classical physics, quantum field theory is the modern calculus, and it is the language of physics. And I copied here this previous slide, this slide changes, the previous slide about calculus, so that we can see the comparison. First of all, it's new mathematics. Calculus was new mathematics. And quantum field theory also exhibits new mathematics. In fact, it's not yet rigorous. So it's so new that we don't even know how to say it rigorously. And I talked a little bit about it earlier. Second, just as in the case of calculus, it was motivated by physics. So again, this is very similar to what we saw with calculus. And it has many applications in mathematics and physics, and I've gone through the various applications in the previous slides. Just as I said it about calculus, I view that as a sign that quantum field theory is a deep idea, an idea that has more applications than it was originally designed for. It was designed to solve some problems in particle physics, and then some problems in condensed matter physics, and then there was cross-fertilization between them. Then it appeared in string theory, it appears in cosmology, and it even has applications in mathematics. So it's very similar to what we saw in the case of calculus. However, quantum field theory fails the maturity test. I proposed a maturity test earlier for a field. Maturity test is whether all books and all courses are more or less the same. That's not the case in the case of quantum field theory. Different books take different perspectives. The order of the presentation could be different. And this is the sign that the field is not yet mature. The presentation has not yet been streamlined. This and many other things tell us that we are still missing big things. Now, let me tell you a little bit more about quantum field theory, so to put it in context. Let me say a few things about quantum field theory and some important aspects of it, which will be important later in the talk. One interesting aspect of quantum field theory is the appearance of separation of scales. In fact, this is common in physics, and not only in quantum field theory. And in fact, it's even an important concept in all of science, including the social science, where we have different effective descriptions at different length scales. This has two aspects to it. One is a simplification. When we study the system at a particular length scale, we do not need to understand all the details and all the intricacies of what's going on at shorter distances or what's going on at longer distances. So this is a simplification. It also means that nature is kind to us. So as we try, at every scale, we have an effective theory of that scale, an effective theory at that scale, and then that effective theory is replaced by a deeper truth happening at shorter distances. So over the centuries, as we explored nature at shorter and shorter distances, it was like peeling an onion, uncovering new layers of more fundamental, deeper structure at shorter and shorter distances. This is known in philosophy as reductionism. So let me give you some examples of it. Thermodynamics was understood centuries ago. It describes phenomena like heat and temperature and so forth. It was later replaced by a more microscopic description in the context of statistical mechanics. Statistical mechanics is, again, well understood, and thermodynamics is an effective description of statistical mechanics. As a second example, let me discuss a little bit about hydrodynamics. I mentioned the Navier-Stokes equation as the equation that govern the motion of fluids. I talked about that when we talked about classical field theory. Now we understand that the fluid is really made out of molecules, and the molecules bounce around. And we could try and keep track of all the molecules in the fluid. And this would be a more complete and more correct description of the motion of the fluid than hydrodynamics. But hydrodynamics is a simpler description that captures the essence of what's going on at long distances, assuming that the fluid is more or less smooth. Over the last year or so, many of us became interested in epidemiology. And again, we see the same thing. The theory at shorter distances addresses what the virus does, how it affects the body, how it multiplies, and so forth. Most of these details are not important if you want to understand how one individual infects somebody else and how the disease progresses from one individual to another. And again, most of the details of the infection, how one person infects somebody else, and what we should do to prevent it, like wearing masks, keeping social distances, and so forth. This is independent of most of the details at shorter distances about how the viruses behave, how the virus behaves and how it multiplies. And also, it's irrelevant if we are interested at longer distances. We are interested in how the overall pandemic evolves, the death rate, hospitalization, and so forth. So we see here again an example of the simplification. At different length scales, we have a different theory, which captures the essence of what's going on at that length scale. And it depends very little, it's not completely independent, but it depends very little on what happens at shorter distances, in the deeper theory underlying. The same thing is true in field theory, and that here the phrase that is being used is effective field theory. And this process of deriving a theory at one length scale from a theory at the shorter length scale is known as a renormalization rule. And these ideas were put forward by Wilson. So unlike the other fields, which have been true for centuries, that we have this separation of scales and effective theories, in the context of field theory, this became an actual calculational scheme. It's more than just a general philosophical idea. It's something that you can turn into equations and you can compute a lot of things. And the main people who contributed to that are Wilson and Weinberg. So let me say a little bit more about that. We have different theories at short and at long distances. The short distance theory is where we formulate the problem. We call it the UV for ultraviolet. It describes the short distance physics. And at long distances is where we read off the answer. So these are, we simplify to just two layers here, the ultraviolet, the short distance theory, and the infrared, the long distance theory. And this has been a very useful way of organizing our understanding and organizing the information. Because at short distances, which is where we formulate the problem, let me give an example in the context of condensed matter physics. We take some atoms, we put them in the box, the atoms interact with each other, they form a crystal, and the electrons move around, and at long distances, so this is what happens at short distances. At long distances, it could be a metal, or at long distances, it could be a superconductor, or it could be an insulator, or it could be compressible or not compressible. Many of the details of short distances, or what happens at short distances, are not important to understand what happens at long distances. The behavior of the system at long distances is independent of many of the short distance theory, and this is known as universality. This is the simplification that I talked about earlier. At long distances, we have an effective theory where most of the details of the underlying structure are not important. Conversely, we formulate this as the problem, and we would like to find this as the answer. So this is like a question. Put atoms in a box, put these atoms, they have this and that interaction. What do they do at long distances? Answer, this is where you read off the answer. And quantum field theory is particularly helpful in describing the long distance physics. Because even if the atoms form a crystal, and at short distances we have a lattice, which is quite typical, at long distances we have a continuum. So the structure of the underlying lattice is not visible when we look at the problem at long distances. And therefore, at long distances, we have a system living in the continuum. This is similar to approximating a sum by an integral. Instead of having a finite number of degrees of freedom, which is very dense, very large number, we approximate it by a continuum. Are there any questions so far, or can I just continue?
Yes, we have two. I think it's a good point to stop. First, VH say, please say something more about the areas of mathematics inspired by KFT.
So I mentioned topology and geometry, also some other fields. I can say more about that. This is not my field, and it's also not the direction I'm heading. So later, if we have time, I'll be happy to give you more information, especially low dimensional topology. What was the other question?
And Fernanda asks, what are the biggest challenges in KFT in 2+1 dimensions today?
What's the beginning of it?
What are the biggest challenges in KFT in 2+1?
The biggest challenges, from my perspective, is to formulate it in a better way and find a new phenomena that quantum field theory can exhibit. And in fact, I'm going to discuss some of that soon. Okay, so let me say a little bit more about the phases of quantum field theory. I say that we formulate the theory at short distances, and then at long distances, it has various phases, and quantum field theory describes the phases. So very roughly, we can formulate it as follows and find the following classification. We put the system in a large but finite volume, and then we look at the Hamiltonian, and we find what the spectrum looks like. And very roughly, there are two classes of possibilities. The first is a ground state. Here, as a function of energy, energy goes up. There's a ground state, perhaps several ground states. And then there is a gap in the spectrum. And then we have a continuum in the spectrum. And there's several more refined classification of whether the ground state is unique or there are several distinct ground states. And a characteristic example here is a free massive particle. You just take one particle. The ground state is no particle at all. And the first excited state is one particle with zero momentum. And then we can make the momentum of the particle larger and larger, and we get a continuum of states. And we can also have at some point 2 particles and 3 particles and so on. So these models are called gap because there is a gap in the spectrum. The second class of models is known as gapless, where there is a ground state, and immediately the continuum stops. An example of that is when instead of having free massive particles, we have, say, free massless particles. Because the gap here is how much energy it costs us to create one particle. And if the particle has zero mass, it doesn't cost us any energy. And then we have such a continuum. Then it could be more complicated. There's further refinement. If the particles are free or interacting. If it's interacting, it's richer. And there are examples of that in nature. And there's further, even more refined classification depending on more details. So this is a summary of what I wanted to say about quantum field theory as we understand it today. And it's still very exciting, and people still find more phases, either of this kind or of that kind. But the point I would like to change direction a little bit now and argue that we know that there must be extensions of traditional quantum field theory. Our understanding of quantum field theory is incomplete because there are systems which look a lot like quantum field theory, but they do not satisfy the axioms of quantum field theory as we understand them today. And examples of that originate from 2 different sources. The first source is from string theory. String theory has Newton gravity in it, therefore it has something like Newton constant, and therefore it's gravitational. But we can take a limit that we turn off Newton constant. If we turn off Newton constant, we turn off the gravitational interaction, and then we are left with a theory without gravity. That means, typically, in that case, we end up with a quantum field theory. I mentioned it earlier, and I said that at low energy, string theory looks like quantum field theory. And this is one of the reasons it is so exciting, because we know that nature is described by quantum field theory. However, there are certain examples, certain space-time backgrounds where this is not the case. But we can turn off Newton's constant, turn off gravity, and we end up with a theory without gravity, but it doesn't satisfy all the properties of quantum field theory. I'm not going to discuss it in detail. I just mentioned 2 buzzwords. One is field theory in the non-commutative space. The second is known as little string theory. These are 2 separate phenomena have some things in common, but many things are quite different. The main takeaway from this slide is that string theory is a consistent framework, and there is a limit of string theory, a corner of the parameter space where it should behave like quantum field theory, but it doesn't. The second class of examples arise from condensed matter physics, and I will soon review them in detail, where people discuss lattice models. I said earlier that often when we start with a lattice, at long distances, it looks like a continuum. We have degrees of freedom on a lattice, and I'll soon give examples. And at long distances, the lattice is washed away. We don't care about the lattice, and the whole thing looks like a continuum. So typically, this is the case, and this is where quantum field theory has been so successful over the last several decades, giving us the description of the long-distance physics of lattice systems. But in certain special cases, that's not the case. And in particular, models of fractals, which I will soon discuss in more detail. So we have two ways of, historically, we had several ways of generating quantum field theories. Some of them is limits of string theory or limits of lattice models typically give us field theories, standard field theories, but in some cases they don't. They give us something new, something we haven't seen before. And although these examples are quite different, there are different examples in string theory, there are different fractal models, but they have some common features, surprisingly. First, they are not Lorentz invariant. They're not even invariant under ordinary spatial rotation. That by itself is not shocking. It's easy to take ordinary quantum field theory and make it not Lorentz invariant, just add a term that violates the rotation symmetry. So that by itself is not surprising. What I find more surprising is that another common thing in all these examples is that we see here UV-IR mixing. This separation of scales that has been dominant in physics over centuries. In fact, not only in physics, I gave example in epidemiology. And in almost every place where there is research, there is this separation of scales. This separation of scales, which turned into a calculational scheme in quantum field theory through the renormalization group, this separation of scale is not present in these examples. And this would be shocking because it violates the law that every problem has this separation of scales. The UV and the IR, or the short distance and the long distance problems, are completely separated. This has been the case in all the examples I mentioned before, and in almost all problems in physics, this is the case. This is not the case in these particular examples. So that should be quite a warning sign if we think that quantum field theory is all there is, because these things do not look like standard quantum field. Now, I mentioned some examples and some common features. There are also many bizarre features that are specific to each model, and I don't yet see them as a common thing. So now what I'm going to do in the coming slides is give a very brief history of, so I'm going to focus now on the second class of examples of these fractals. And the first thing I will do, I'll give a brief history of fractals, of how we got to where we are, and then I'll give more details about the history, and then I'll talk about more modern developments. So let me start with the brief history of fractal models. The original papers appeared in 2004 by Shamon and in 2011 by Ha. Notice that they're 7 years apart. These papers were motivated by questions and ideas in quantum information theory and computer science. So I decided to copy the titles of the original papers to show what the authors were interested in. So it says quantum glassiness in strongly correlated clean systems, an example of topological overprotection. And Haas paper is called local stabilizer code in 3 dimensions without string logical operators. So that happened in 2004 and 2011. The next step is in 2015. So this is 4 years after Haas paper. The realization sank in that these models are also significant as new phases of matter. So this is what happens in 15 and 16. There are these 2 papers. And in these 2 papers, these authors presented many more examples of fractals. I will soon discuss these specific examples. And again, I quoted the titles so that you could see that the emphasis is different. These look more like physics papers. A new kind of topological quantum order, a dimensional hierarchy of quasi-particles built from stationary excitations in fractal topological order, generalized lattice gauge theory, and duality. So these were these papers. These models, the models that they discuss, are a lot simpler than the previous models. And it also became clear that there are more examples, because once you have one example, you don't know what to make of it, but when there are more examples, this opened the floodgate, and many more examples were found. These models were gapped. So people also found gapless models, and they are associated with, with some strange gauge theories. I will describe that soon. And other development is that there were different constructions of the models, some of them in terms of layers of decoupled theories. Decoupled theories in 2+1 dimensions, you couple them together to make a theory in 3+1 dimensions. And it also generated connections, and it related to ideas in other branches of science, in particular elasticity, quantum information. In fact, this is where the idea started, topological quantum field theory, and others. Now, this is a very large field, and I cannot do justice to it, but this was kind of a brief history of this subject. So let me discuss it in a little bit more detail and focus only on two examples. Actually, three examples. The first of them is the X-cube model. This is one of the papers, these three authors that I mentioned earlier. They consider a three-dimensional lattice, this is space, and they put a spin up or spin down, it's called a Z2 spin or a qubit, on every link of the lattice. And the Rotary Hamiltonian. And the Hamiltonian here is very specific and very concrete. There's two kinds of terms. One is a sum over all the cubes, where you go through every cube and you multiply the sigma 1, Pauli sigma 1, that acts on every link of the cube. So you go link by link around the cube, you multiply all these operators, and this is one operator here, and then you sum it over all the cubes. The second interaction uses sigma 3 on these links. This is Pauli sigma 3 that anti-commutes with sigma 1. And for every site on the lattice, you look at the XY plane, and you multiply sigma 3 with these four sites. And then you repeat that in the this is the XY direction, the XZ direction, and the YZ direction. So you have three such terms. And you sum that over all the sites. Now, the details are not important for the purpose of this colloquium. They're very important in order to get the physics right. But what I do want to emphasize is that this Hamiltonian is innocent. It uses Z2 spins. A lot of models are made out of Z2 spins, for example, the Ising model. And there are some interactions, short-range interactions. You multiply the spins at different nearby points here on the links. So this does not look like something which would be pathological or something that would look unusual. Yet, this model as it stands is exactly solvable. And these people solved it. And the conclusions were the following. Every one of them is surprising. If you formulate the problem on the lattice with Lx sites in the X direction, Ly sites in the Y direction, Lz sites in the Z direction with periodic boundary condition, you find that there is a huge ground state degeneracy. The number of ground states is 2 to this power that grows linearly in the length. This formula is shocking. It's shocking for several different reasons. First of all, the number of ground states in the system depends on the number of lattice sites. That's very unusual. Usually a system has one ground state, or it could have finite number of ground states. That's already quite peculiar, that there's more than one ground state. But here, if we make the number of lattice sites larger and larger, make it a macroscopic number, then the number of ground states is exponential in this number. In other words, if we take such a lattice and we just add one more layer and make Lx bigger by 1, the number of ground states is multiplied by 4. So it's a huge ground state degeneracy. Also, the exponent here, which can be thought of as the entropy of the system, is not extensive. It's not proportional to the volume. It's proportional to the length. it's sub-extensive. Normally, this is a number. The number here in the exponent, the entropy is a number. This is the entropy at zero temperature. Here, it is a sub-extensive quantity. The next thing which is funny here is that if we try to take the continuum limit, namely the number of lattice sites to infinity, making the distance between lattice sites going to zero such that the system has finite length. In other words, we try to approximate, imagine this is a material, we say it is 1 centimeter cube, take such a cube, 1 centimeter cube, and the number of sites, these L's, goes to infinity. In that case, in that limit, the number of ground states is actually infinite. And the ground states reflect short distance physics. This is actually obvious from what we said here. The very fact that the number of ground states depends on how many sites we have means that we add another layer to make LX bigger, the number of ground states grows. This means that the properties of the ground states depend on short distance physics. It depends on how many atoms or how many sites are on lattice space. This is the celebrated UVIR mixing that I mentioned earlier. Also, these people found that the spectrum is gapped. So there are these ground states, many of them, but then there's a gap in the spectrum. And the Hamiltonian is stable or robust. So they studied a particular Hamiltonian, but if you deform this Hamiltonian, you add more terms to it. As long as the coefficients are sufficiently small, but they can be non-zero, the answers that I mentioned so far do not change. The ground state degeneracy is not lifted. And the system has localized excitations, which look like particles that can move around, but they have restricted mobility. They are particle-like excitations that are known as fractals. They are fixed at the point. They cannot move from point to point. Even if you give them a lot of energy, they just sit there. They cannot move elsewhere. If you give them a lot of energy, a particle can split to several particles, say 2 particles, 3 particles. In this example, 3, so it can split, but they cannot move. There are also particles that are called linons that are fixed to move on a line, in the x direction, the y direction, or the z direction, but they cannot move out of it and move diagonally. Oops. This is a Mojda. Oh, wrote something on my screen. And there are planons that are fixed to move on the plane, either the xy or the yz or the xz plane. It's again very peculiar. This is not something we're familiar with. Then, going back to an earlier paper, Haas paper, this was Haas code, and Ha put 2 spins, 2 qubits at every site of the lattice. And again, there's some structure of the lattice. The details are not important. Oops. The details are not important. We have sigma 1 and sigma 3. The details are not important. The important thing I want to emphasize is that the Hamiltonian has 2 kinds of terms, and it's again an innocent-looking Hamiltonian. A Hamiltonian which has spins. Here we have 2 spins per side, and there are interactions which are not nearest neighbors, but only finite distance away, and that doesn't look that crazy. Yet the model has many bizarre properties. Again, the ground state degeneracy is quite complicated. It's 2 to a power, but that power is much more complicated than before. It's a number theoretic function of Lx, Ly, and Lz. Before it was a linear function, and now, even if we take all of them to be equal, it's still a complicated function. And this function is not even monotonic in L. So we add another layer to the lattice, and suddenly we lose most of the ground states. We add another layer to the lattice, we have many more states. As in the previous example, it's bounded by L, but since it's not monotonic, the limit L going to infinity is not well defined. As L goes to infinity, it can grow linearly in L, as in the previous example, or the limit would be finite. What this means is that the limit L going to infinity is ambiguous. So in these systems, when we try to ask what happens if the number of sites goes to infinity, the answer turns out to be ambiguous. So it really begs the question, is there a continuum limit? Can we think of these theories in terms of the continuum field? The other development that I mentioned earlier is due to Pretko, who considered gapless models. It was motivated by earlier papers by Shu, who proposed a change in the ordinary gauge symmetry of Maxwell theory. Maxwell theory has a scalar potential. Maxwell theory is called A0. And under gauge transformation, it is shifted by the time derivative of the gauge parameter. And then we have a vector potential, which transforms with the spatial derivative of alpha. In Schu's model, the vector potential is replaced by a tensor potential, and it transformed by a double derivative of alpha. So we can follow our nose and construct an electric field and a magnetic field. You can check that these electric and magnetic fields are invariant. You can write a Lagrangian or a Hamiltonian, which is E squared minus B squared. And we can look for the spectrum, and it has some kind of photons, but photons with a very peculiar dispersion relation. What Pretko noticed is that Gauss' law that comes from such a gauge theory is not a divergence of E. After all, E is a tensor, but its double derivative of E is the charge density. And therefore, if we work in infinite space and we integrate this over space, it's a total derivative, and therefore it depends only on what's going on at infinity. And therefore, it is conserved. This is in standard math, as in standard math. But since we have here a double derivative, we can put here an xi. And again, we can integrate by parts. And this again depends only on what's going on at infinity. And therefore, the dipole charge is also conserved. So what Pretko noticed is that in this particular system, both the charge density and the dipole charge are conserved. This means that the excitations have restricted mobility. So if we have an excitation, it carries some charge. It also has some dipole charge. If we try to move the excitation to a different location, the total charge is not going to change, but the dipole charge will change. And since the dipole charge is conserved, particles have restricted mobility. So all these ideas lead to many questions. First of all, are there more examples? Because people just stumbled on these examples almost by accident. Are there more examples? Examples with even more bizarre phenomena or exotic phenomena. We could also ask, people found these examples at random, what is the underlying reason for this? What's the deep reason that leads to this behavior? Examining the model without solving it, can we tell whether it has this bizarre behavior or not? More generally, again, as I keep saying, people found these examples at random, and every new example has new phenomena. How should we think of this whole set of examples? How are we going to classify them? What are the possible phases? How are we going to organize them? And in ordinary systems, this is what quantum field theory was so powerful and so useful. The long distance behavior of the system was captured by quantum field theory. Here, is there a variant of quantum field theory that does the job? Is there a variant of quantum field theory that gives us such an organization or classification of these systems? And there are many more questions that we could ask similar to these. So we're going to look for a low energy continuum field that does the job. And it's clearly going to be challenging because just superficially looking at it, it's clear that it's not going to be easy. Because, especially because of this UVIR mixing, the fact that the properties of the ground state depend on what happens in very short distances, this is the hallmark of UVIR mixing. What happens at long distances depends on a lot of details of what's going on in short distances. This is unlike what we are used to. So if we would like to accommodate this structure in quantum field theory, something will have to give. We'll have to bend the rules slightly so that it works. However, this looks almost impossible because quantum field theory is a very delicate structure It barely manages to make sense. And now we say that we need to deform it a little bit. We need to extend the framework a little bit, hoping that it still makes sense. So it looks like a non-starter. Should we even start doing it? But there's good reasons to try and do that. And there are twofold. First of all, if we have some kind of a continuum field theory description or a generalized continuum field theory description of the system, this will give us insight into how to organize and classify the systems. Maybe it will give us some other examples. And the other thing is, and even if you're not interested in this particular system, this will teach us something new about quantum field theory, because all these examples mean that our description of quantum field theory is not complete. So this is the research I embarked on with fantastic postdoc Shuhei Shao. And we found some way of extending what we normally do in continuum quantum field theory, such that we can accommodate these theories. And our theories had several new elements in our continuum theory. Some of them are not surprising and others are more surprising. First, space-time symmetries. Normally in quantum field theory, we consider systems that are translation invariant, and rotation invariant, and Lorentz invariant. Our systems are not Lorentz invariant. That's not a big deal. Almost every system in condensed matter physics is not Lorentz invariant. Also, not rotationally invariant. We only have rotational invariance under certain discrete rotations. That I do not view as a big deal. Second, we imposed exotic global symmetries and then we gauged them. I've already mentioned some of these exotic gauge symmetries before, and I'll still say more about them. The most surprising thing we needed to do, and in fact it was forced on us, is to consider fields which are discontinuous. Now, on the lattice, everything is discontinuous because we have fields at different points on the lattice. And there's no notion of continuity because what degrees of freedom do at one side of the lattice is independent of what they do at another side of the lattice. In the continuum, typically all the field configurations are smooth. We have in mind some kind of a smooth configuration. So we specified exactly what kind of discontinuities and singularities we allow. Things are more continuous than on the lattice, or not as discontinuous as on the lattice, but they are more discontinuous than what we normally do in field. And yet the answers are universal in the sense that they are independent of most of the details of the lattice, but not all of them. So here is a typical example, tensor gauge theory. It's a variant of the tensor gauge theory I mentioned earlier. I had a scalar potential, A0, which transforms as a gauge theory like D0 alpha. And instead of vector potential, we have a tensor potential, which transforms like the double derivative of alpha. But unlike the model I discussed earlier, we take I not equal to J. So we restrict the allowed tensors. And again, we have an electric field and a magnetic field. I don't anticipate people to follow all the details, but you'll soon see where I'm heading and why I think this is interesting. So you write this model, and you can write the equations of motion, and you can look for the dispersion relation. And this is the dispersion relation. And since we have double derivatives in the electric field, in the magnetic field, we have terms here with more complicated momentum dependence. The key point is that if Kx and Ky are 0, no matter how large Kz is, W equals 0. Because if Kx and Ky are 0, this is 0, and this is 0, and this is 0. So W equals 0 is a solution of the dispersion relation. What this means is that for generic momenta, low energy is the same as low momenta. That's the same thing we're familiar with. Low momenta is low energy. But there are some regions in momentum space, specifically Kx equals Ky equals 0, where we can have zero energy state with arbitrarily large momentum. This is the UVIR mix. And this is the key to the peculiarity of these models. So the key to the peculiarity is that even if we limit ourselves to zero energy, and even excitations with low energy, they are sensitive to what happens at very arbitrarily large momentum. It also means that we have an infinite number of zero energy states. This is actually not a trivial statement because one has to check it more carefully in the quantum theory and make sure that this is indeed the case. Let's discuss the gauge transformations of this theory. The gauge group is U1, so alpha is periodic. Normally in ordinary gauge theories, the fact that alpha, gauge parameter, is periodic, it leads to fluxes. We can have magnetic fluxes in magnetic monopole fluxes. Here we allow certain discontinuous gauge transformations, and I just wrote a formula for one of them and with a heaviside theta function. So this function jumps in y, but smooth in x. This term jumps in x, but smooth in y. And with such gauge transformations and transition functions, we find quantized classes. Next, we would like to consider a Zn tensor gauge. So we take the U1 theory and we turn it into Zn. So we use the Higgs mechanism to do that. I'm running out of time, so I'm going to go fast. We are considering the same theory, but the gauge group is not U1, but Zn. And this theory has various dual descriptors. We can use duality to map it to other systems. And a careful analysis of the continuum theory leads to the following properties. First of all, the spectrum is gapped. So there are some number of ground states, and then there is a gap in the spectrum. Second, there is an infinite ground state degeneracy, and if we regularize it with the lattice, the number of ground states is this form. Next, we have particles with restricted mobility. So they are particle excitations, and they have restricted mobility. There are also no local operators acting in the space of ground states, and therefore the system is robust. You can deform the system any way you want, as long as the coefficient is small enough, the answers don't change. And there's also a rich spectrum of line operators. This is the continuum field theory description of the Zn version of the X-cube model we have presented earlier. They discuss n equals 2, and here we put arbitrary n. This brings me to the end of the talk. Toward the end, I kind of took off a little bit. Let me summarize it. We had a long journey, starting with Newton and Lagrange and going through Maxwell and Einstein and classical physics and quantum physics. And then we talked about quantum field theory. We showed that quantum field theory appears everywhere. I advanced it as I propose that it should be thought of as the language of physics because it appears everywhere. Over the last several decades, there has been a lot of progress, but there are also many big questions. And constantly there is excitement because new phenomena are being discovered. I also mentioned that some string theory constructions and some lattice models lead to very peculiar systems. I mentioned the non-commutative field theory and the little string theory coming out of string theory, and theories of fractals coming out of lattice systems, and for all we know, there could be many others. And the common thing about them is that they do not fit this language of quantum field theory. So we need to extend our understanding of quantum field theory. Some of the phenomena, the main phenomenon that I emphasized is the UVIR mixing, this phenomenon of separation of scales, which is so common in quantum field theory, which is also very common everywhere in science. This is not present in all these examples, both in the examples coming out of string theory that I did not discuss in detail, and in the example coming out of these fractals. We saw a large ground state degeneracy. The number of ground state grows with the number of sites, so it depends on what happens at short distances. And sometimes it's so, the dependence on the site is so complicated that there isn't even a well-defined limit as a bit infinite, but not even an infinite well-defined limit as L goes to infinity. And this part is closely related to the fact that the observables are discontinuous in the continuum limit, and therefore we have no choice but to use discontinuous fields. The other peculiarity of these systems is the excitation with restricted mobility, particles that are fixed at the point or are restricted to be restricted to move along a line. And all these properties seem to be incompatible with the framework of continuum quantum field theory. So this is a big challenge, and yet we try to accommodate these ideas in quantum field theory. So we presented non-standard continuum quantum field theory. I presented only one or two of them here. We have, I think, by now 24 different such examples of different kinds. They are invariant only under discrete rotations. They have exotic globals and gauge symmetries. I mentioned that. And this is the key point, that the field and the gauge transformation parameters can be discontinuous and even singular. They are not as discontinuous as in the underlying lattice, but on the other hand, they are not as continuous as in standard quantum field theory. And these continuum field theories manage to capture the universal behavior of the lattices. So they do the job. They reproduce the long distance physics, they reproduce the ground state degeneracy, and they reproduce the properties of both particles and their restricted mobility. So I'm out of time, so I'll thank you and please stay healthy. Thank you.
Thank you, Professor, for the colloquium. We received some questions at the chat on YouTube. Unfortunately, due to the time, we are not able to respond all. But thank you for the participation. We have now the discussion with graduate students at Zoom.